Back from our break, let's roll right into our next set of pitches. Our next finalist in sensing is Spyros Gallis from SUNY Polytechnic Institute. Please unmute yourself for a mic check. When you're ready to begin, Spyros, please click the Start Presentation button on your screen and your 10-minute presentation will begin.
Good morning, everyone, and thank you for attending this very intriguing virtual event today. I'm very excited to present my group's research proposal today on the design, development, and fabrication of novel solid-state single ions for quantum plasmonic sensing. So I'm going to start off with the research motivation, the vision, if you like, behind our research proposal, which is to demonstrate on-demand integration of erbium ions that emit at a technologically important wavelength of 1540 nanometer in nanophotonic structures. And these structures are composed of an array of ultra-thin nanowires, which are effectively coupled to plasmonic nanocavities, as you can see on the left and the right-hand side of this figure. We will then leverage these devices to study their light-matter interactions and then engage these two concepts in order to realize a scalable on-chip platform for quantum sensing. So what I've just described, and I think to make it a bit more digestible for you, is illustrated in this cartoon, the main panel, where you can see that the single photon emitter, depicted as the red sphere, can act as an isolated quantum system. For example, it can interact with an external electromagnetic field at nanometric proximity, and this interaction can cause a detuning between the emitter and the cavity, which can result in the modulation of its photoluminescence. So we can use these kind of interactions to establish quantum sensing for electric, magnetic field, strain, and temperature. Moving forward to the second panel, here the question is, what is the technological and also scientific, if you like, gap that we're trying to fill with this proposal? So recent research efforts towards the development of a scalable solid-state quantum devices, such as quantum sensors, single photon source, if you like, have been hindered by the lack of available fab-compatible material platforms for one, and by the need for high sensitivity and high spontaneous emission rate, which both require the accurate placement of single emitters in the device. So what we propose here in order to address these challenges is a deterministic integration of erbium ions in fab-compatible silicon carbide nanowires, and also into the nano-sized mode volume of plasmonic cavities, which can substantially enhance the spontaneous emission rate of erbium ions. So somebody may say here, let me scroll down. So somebody may say here, okay, this sounds very promising, but what is the innovation that you bring on the table which can make this happen? So let me address this by saying we have recently demonstrated in nanophotonics state-of-the-art high accuracy placement, less than 10 nanometer, of erbium ions in defect-free silicon carbide nanowires. These two demonstrations are key building blocks towards the development of next generation of scalable on-chip quantum devices, which will require the proper engineering of the single emitters, and also will require the minimization, if not reduction, of defect densities in these devices. This becomes even more important. Let me scroll down. If you consider the challenges which are associated with the integration of, let's give me a second, of single emitters into optical resonators, including plasmonic nanocavities. For example, efficient coupling to these devices requires the accurate engineering of both the position and also orientation of these emitters. So let me click on this figure. So this can be seen in this figure where our numerical calculations as predicted, as expected, show that the partial factor decreases substantially in figure B here, with increasing distance between the emitter and the metal. And the same applies for the orientation of the emitter in figure C, with respect to the cavity. Here, 0 degrees corresponds to the direction parallel to the length to the axis of the nanowire. So how are we planning to tackle these two challenges? For one, the nanometer scale proximity between the emitter and the cavity can be satisfied, can be met due to the ultra-thin dimensionality of the proposed nanowires, which is less than 10 nanometer. And this is well within our reach of nanofabrication strategies. Now, as far as the orientation is concerned, we can take advantage of the anisotropic dimensionality of our nanowires, where the width of the nanowires is much smaller with respect to the emission wavelength of erbium ions, 1540 nanometer again, and that results in an anisotropic absorption and emission behavior for the erbium ions. Let me show you the next figure. So this is presented in the last figure in this panel, where we have demonstrated preferential polarization emission from the nanowires, again, due to the anisotropic dimensionality of the nanowires, in contrast to the expected isotropic emission behavior when erbium ions are implanted in bulk thin films, which is the bottom part of this figure. Now, I would like to slightly switch gears and move into the two major tasks associated with our proposal. So in task one, as already mentioned, we plan to demonstrate deterministic placement of erbium in silicon carbide nanowires by leveraging our scalable and powerful fabrication strategies recently developed in my lab, and also by taking advantage of our unique capabilities at SUNY Poly, which includes our ion implantation technology. We have successfully demonstrated integration of an ensemble of erbium ions into ultra-thin nanowires, 10 nanometer. And another key property of these nanophotonic structures is that they exhibit an absorption cross-section for erbium ions, which is 2 orders of magnitude larger than typical benchmark values in erbium-doped bulk materials. So this is another important photophysical property which was enabled by our novel nanofabrication and defect density, reduction of defect density, and also device design. We will then experimentally, if you scroll down, we will experimentally measure, characterize these nanostructures by means of photoluminescence spectroscopy and also by underbalancing measurements using our single photon microscope system, which is equipped with state-of-the-art superconducting nanowire detectors. In parallel, we plan to investigate the emission properties of erbium as a function of the local environment by means of electron paramagnetic resonance. Now, regarding task 2, here we aim to investigate the light-matter interaction in these hybrid nanowire-based plasmon devices using our integrated methodology, which includes both numerical calculations and modeling, and also the fabrication of corresponding prototypical devices in an iterative manner, with the vision, the goal, if you like, to demonstrate distinguished electric and magnetic field enhancement. It is worth highlighting here that the parameters used in these simulations and modelings, including the results I'm presenting today, are well within our reach of our nanofabrication strategies and tolerance. So to this end, here I'm presenting in this figure our numerical calculations for one of our device design, where you can see that the maxima and the electric field enhancements are well separated in the cavity. As a matter of fact, if you look at the right-hand side, the top panel, this separation is more than 120 nanometers. So, and this is another manifestation, if you like, evidence of the feasibility of our proposed tasks. To this end, distinguishable electric and magnetic field enhancements can be used as atomic scale probes for quantum sensing of electric and magnetic fields. So in conclusion, instead of a long epilogue, if you like, I'd like to say that ultimately this research proposal aims to revolutionize the development of scalable on-chip quantum sensing and also on-chip biological sensing, considering that the emission of erbium is in the near infrared region of the electromagnetic spectrum, which is well positioned for biological applications. And with that, I would like to thank you all for your attention. Thank you very much.
Thank you. Paper is now open for 5 minutes of questions.
Hi, this is Carl Williams. Let me ask a quick question. So can you expand a little on some of the defense applications that this technology would have and might have?
Yes, let me, first of all, I mean, this could be used as for magnetometry.
So this is Mintari. I'm just thinking about what your like post-implantation annealing process would be like, because it's really tough to do ion implantation, and very few fab labs can do this well to potentially remove damage. So how is the facility there able to handle that even at SUNY?
Yeah, this is a good question, and I think this is one of the I believe one of the key properties that we have demonstrated with this novel nanofabrication. Number one, there is a lot of complexity in terms of explaining, but just because of the ultra thin dimension of the nanowires, this allows for low passivation, if you like, and erbium activation temperatures, therefore diminishing any kind of erbium ion diffusivity. That's number one. And number two, just because we use certain sacrificial layers, let me put it that way, again, damage on the actual sample is minimized. And this was demonstrated through, again, the benchmark value that I mentioned about the absorption cross-section, which is enhanced by 2 orders of magnitude with respect to regular typical values in erbium-doped quantum materials. And by time result for the luminescence measurements, where we did not see any kind of change in the lifetimes between high and very low and cryogenic temperatures.
I'm assuming that's how you deal with erbium clustering with your separation there, and potentially.
Correct.
I see. And thermal quenching issues, perhaps? No.
Not really, no whatsoever. That's another, I would say, beauty of the proposed and demonstrated work. I mean, I have a link in our recent paper in nanophotonics where we elaborate more on some of your very good questions. But no, we did not see any kind of temperature quenching or even concentration quenching by the bioimplantation.
Thank you very much. We'll end it right there. So once again, thank you, Professor Gallis.